All right. So today is our last day of rigid body velocity and acceleration analyses. So we can move on next week. Remember, we're learning all about motion of these rigid bodies, their translation and their rotations, coupling those two things together. And we're really doing that so that we have some tools to use with F equals ma, Newton-Euler methods, sum of moments. We've got techniques that we can then use with work energy. So we can track velocities and angular velocities. Same thing with momentum. We need to be able to track velocity and angular velocity. So the whole thing is like, this is just helping us for these next couple weeks to push to the finish. So let's get rolling. So today we'll do acceleration analyses. We've kind of set the stage for this already, actually, like last week. So we'll look at, really, we have two approaches for acceleration analysis. We've got this instantaneous approach, which we call the vector method, very much like what we've been doing the last few days for velocity. And then the second one is the differentiation of geometric constraints. But we're not talking about that one today because we kind of already did that. We said we set up a problem where we defined two components, maybe an x and a theta. We took their time derivatives. We had velocity from that. We took a second derivative, we got to acceleration. So the second thing here, differentiation of geometric constraints, totally valid. It's nice because it can look at a whole bunch of different times and a whole bunch of different geometries, but it's pretty simple. Hey, we took one derivative in time to get to velocity, take a second derivative to get to acceleration. And we already did an example of that. So the vector method, very similar mechanically to how we do it for velocity analysis. So a little primer on what we did for velocity. We had our blob. We have 2 points on said blob. We could write the velocity of B is the velocity of A plus the velocity of B relative to A. Okay? So we looked at these. We said, well, what is all this stuff? Velocity of B. That was our time derivative of the position of B. Velocity of A. That was our time derivative of the position of A. And then this little monster, velocity of B with respect to A, that's the one that needed a little bit of work. So velocity of B with respect to A, we said this was, right, the time derivative of the vector from A to B. And then we thought back to derivative of a vector, which we learned in chapter 2, I think. We said, hey, derivative of a vector is the magnitude part, time rate of change of r, times its original direction. This is from A to B, plus the rotational term, omega AB, crossed with the original vector, r from A to B. So this was just, let's call it section 2.4 in the book, derivative of a vector. And we took a peek at this. We said, hey, for a rigid body, this blob doesn't change its shape at all. The length from A to B, r dot, that's going to be constant. So this term, poof, falls away. So this is really only the second piece. So the velocity of B was equal to the velocity of A plus the angular velocity of the body crossed with the vector between the two from A to B. This body's got some omega too. And we put that to use, and we used it over and over again. Hey, today's acceleration. Let's take one more derivative of this and see what we get. So if we want to get to acceleration, take a time derivative. Velocity of b goes to acceleration of b. Velocity of a, acceleration of a. Now, we've got to use product rule. Derivative of the first piece times the second, plus the derivative of the second piece times the first. So the derivative of the first piece, the time derivative of the angular velocity is angular acceleration multiplied by the second piece plus the derivative of the second piece times the first. Omega AB crossed with r vector dot from A to B. Hey, we just did this. That's what we said we had. And that's why I went through it again, right? So, take that, plug it in. The acceleration of B is the acceleration of A plus the angular acceleration of the body, alpha, crossed with the vector between them, A to B, plus omega crossed with omega crossed the r vector. And there we go. Now we have the acceleration for 2 points on a rigid body, relating them to the angular acceleration of the body and the angular velocity of the body. So this is true in general. If we're looking planar, 2D problems, this thing simplifies to minus, scalar now, minus omega squared multiplied by r from A to B. So you can prove that to yourself. You've got some I, some J, some K. If your omega is in the K direction, and your r vector lies somewhere in the xy plane, hey, run that cross product twice. You'll get this. Once omega isn't perpendicular to r anymore, like you look at 3D stuff, then you got to go back to the full case. But for the planar 2D case, what we're going to do in this class, the acceleration of b is the acceleration of a plus the angular acceleration crossed the vector a to b minus omega squared r from a to b. For my money, if I can drop out a double cross product and just do a scalar value multiplied by a vector, I'm going to do that. Save myself a little bit of time. All right, that's that. All right, we want to take this idea now and start applying it to different systems. One that we're going to see all the time coming up for these next few weeks is roll without slip. So if you've got a wheel and it's spinning on the ground and the bottom of that wheel isn't sliding relative to the surface, it's always just in static contact with it, that's going to be our roll without slip condition. So let's talk roll without slip. So we've got the ground. We've got the middle part of our wheel, point O, that's riding along the surface, or center of our wheel hub. We've got point P at the very bottom of the wheel. Point Q is on the ground. That part's not going anywhere. So if Q is on the ground, that acceleration of Q is 0. Not very exciting. The ground isn't moving anywhere. If we take a look at what's happening here, if we're traveling in the way I've got shown here with x, y, our point O is moving horizontally, right? It's not coming up or down. It's just kind of cruising in a straight line. So I think we can look at this and say, hey, the acceleration of O is going to be some acceleration in the x direction plus nothing in the y direction. We're not changing our position. So our position is staying constant. Its velocity and acceleration are only in that path. The other part we got to look at is the acceleration of p, the point that's in contact with the ground. So for this one, you think what we did with for roll without slip, and I kept walking around and showing you my shoe on the ground, and that has zero velocity relative to Earth, so the velocity there is zero. And the idea is kind of true for acceleration. The acceleration at point P in the tangential direction is zero. So we're not accelerating with respect to this surface in the tangential direction, which would be x in this case. But this wheel's rotating with some omega. So we got to think back to, hey, remember what we did for polar and what we did for NT systems, and we looked at their accelerations. And for a point that was spinning, it had this normal acceleration that we had to deal with. So that normal acceleration, this was I'll call AP sub y. It's not going to be zero, but it kind of looked like a v squared over rho, or an omega squared r for my acceleration of p. We thought, hey, when something's spinning, rotating, with some angular velocity omega, it had an acceleration that pointed towards that center of curvature. So this is a little preview. That's what it's going to look like, but we'll figure that out later. So think last time we got together, we related our velocity at O to our angular velocity multiplied by r, right? We said that, hey, our velocity at O was minus omega r, and in this case it was the I direction, right? This was last time. And what do we see from this? We saw that for an XYZ system where we did the right-hand rule and we rotated our z direction positive counterclockwise, that would make the velocity look like it was going to the negative I direction. So if I swap the sign on omega, I get my velocity in the positive I. We'll see this kind of idea happen again, but not for angular velocity, but angular acceleration, because we also assume the same direction for alpha, positive counterclockwise. So let's try to write our acceleration of O with respect to P, the 2 points that we kind of know something about. My acceleration of O is equal to my acceleration of point P plus what we just worked on. Angular acceleration of the body crossed with the vector from P to O minus omega squared times our r vector from P to O. So just putting this equation for acceleration to use now. What is my r vector from point P to O? That's pretty easy. I'm just going the radius up in the positive j direction. So that guy is not too hard. So substituting in what I know, I've got a of 0x in the I direction plus nothing in the j direction. That's my acceleration of the center. It's equal to my acceleration of p, which we said was 0 in the I direction because it's connected to the ground, plus I'll just call this AP sub y in the j direction for now. Plus, what do I got left? Alpha in the k crossed with my r vector, which I just wrote as r in the j, minus omega squared times my r vector again, r in the j. All right, one little cross product to do. K cross j, it's minus I. All right, now all we need to do is pluck terms. Take the I terms, take the j terms. In the I direction, a0x, and on this side, minus alpha r. Hey, that's just like what we had for velocity. My velocity at the center is equal to the angular velocity times the radius. My acceleration at the center, at that pinned hub, is equal to the angular acceleration times the radius. That's nice, right? Little symmetry there for us. In the j direction, I've got nothing on the left-hand side. And then I've got AP sub y from this. And then I've got minus omega squared r. So this says the acceleration of p in the y direction is omega squared r, which is kind of what I hinted at earlier. And if you wanted, you could relate that to velocity instead, because I got a relationship between v0, or velocity of the center, omega and r. This would also be v squared over r. So depending on what kind of information you're given, if you're given the angular velocity of the wheel, this is going to be an easy way to find the acceleration. If you're given the velocity of the center of the wheel, that's going to be easier. Velocity at O. All right, that's all we need to learn today. We got the acceleration from a vector. Our one equation to use, and kind of a flash into like next week and the week after that is, once we start doing Newton's Euler methods, so sum of forces, sum of moments again, when I push on something in the x direction, I need to figure out what its acceleration is in the x direction. This is where we're going to take this into account. Maybe I don't know the acceleration at the point I care about, but I know the acceleration somewhere else. So this is going to help us transform to get to where we need to be. All right, we already did that. All of my answers are the same, but if you guys like to compare my notes to what happened here, I switched O and P. Just put them on opposite sides, so it looks like my notes will be slightly different than what's on the screen. All right, so when we start putting these systems together, these different linkages and multiple components, we're going to go about it the exact same way we did for velocity, where you might have something that looks like what we have on the screen here. Hey, maybe I know the velocity of C. I know this guy's pinned. I'm going to write two expressions for B. I'm going to write a velocity expression for B for rigid body AB, this side. I will write a second expression for the velocity of B for rigid body BC, this side. I will then use the fact that B is pinned together. Its velocity has to be shared to solve for velocities everywhere. Hey, same exact thing for accelerations, right? Point B is pinned between these two bodies, so I'm looking at just a point. Its acceleration has to be the same whether I'm looking at it from the AB side or the BC side. So we'll do the same thing we did there. We'll link up the accelerations at B for these two rigid bodies. So for this thing right now, A, B, and C. Right? Without solving this all the way, you think, well, I got one rigid body here. I got another rigid body here. That's two expressions, right? I can say the acceleration of B is equal to the acceleration of A plus the angular acceleration of this body, A, B, crossed with the vector from A to B, minus the angular velocity squared of that rigid body, AB, multiplied by the vector between them. Right? Same thing for the other side. A of B, this is for AB up top, and this is for BC down below. Now I have the acceleration of C plus the angular acceleration of body BC now, crossed with the vector, not from AB, but from C to B, minus the angular velocity squared times the vector between them. All right. So same idea. Maybe I need to figure out, I got some angular velocity alpha, or angular acceleration alpha, angular velocity omega. I've got geometry. I want to figure out VC in the x direction. Well, work your way from what you know to what you're trying to figure out. Okay? Like, maybe I don't want the velocity, but I want the acceleration of C in the x direction. You think, I got acceleration equations. I'm going to solve this so fast. Doo, doo, doo. And then you realize, these pesky omegas. So pretty much, if I'm asking you for acceleration of this point, you're going to have to start with velocity. Start with your velocity of these. So my velocity of B, velocity of A, plus omega AB crossed with the vector between them. Do it for the other term too. Velocity of B from the other rigid body. Velocity of C plus angular velocity of the body, omega BC, crossed with the vector from C to B. So if I'm asking you for accelerations, because you need those angular velocities to figure out what they're going to be, you need to start with your velocity analysis. What else do I want to tell you? Oh, yeah. So last time we got together, we talked about this instantaneous center of velocity. And hey, if I know the velocity of some point, we can kind of think about, at some instant, it looks like it's rotating about this point. And we can solve for that location. So that exists for velocity because if we're traveling about a pinned location, the velocity is always going to be perpendicular to that pinned location. Even if it's an instantaneous center of velocity, in that moment in time, that's where its pretend pin would be. Acceleration, it doesn't exist. So acceleration, I might be speeding up. I might be slowing down. And the fact that we're traveling this curved shape about some point, we're going to have some normal acceleration. V squared over rho, right? So your combined acceleration, I don't know, could be in this direction, could be in this direction. Long story short, it's not going to be perpendicular or a way of locating it with respect to an instantaneous center. So while we have instantaneous center that helps us on the velocity side, this idea doesn't hold up for the acceleration side because we've got these two components we need to worry about, the tangential acceleration and the normal, and that screws it up for us. So. Okay. So gears. Gears are just like the ground. Without going into this too much, I could have drawn them this way. So when we did gears for velocity, we said that whatever is happening at this meshing point between A and B has to be shared, right? For these gears not to be grinding, the velocity at the point that they're touching, it's got to be the same. Same is true for the acceleration in that tangential direction. This is kind of like the same idea we just used for roll without slip on the ground. Hey, the ground isn't accelerating in the tangential direction, so the bottom of your wheel better not be either. Here, these gears got to be accelerating together, because if they weren't, you'd be missing some teeth, right? They'd be grinding really bad. But I stopped short of saying the entire acceleration is the same at these gear points. Because when they mesh, remember about that normal acceleration business. Omega squared r is my normal acceleration, pointing towards the center of curvature. So on B, not that I can, no, that's a center, it would be pointing down. So this would be omega A squared times RA. This would be omega B squared times RB. You think that? Right away you should be able to see that, hey, they're not going to be the same because they're pointing in opposite directions, right? And don't do this either. Just because they're pointing in different directions, they're not the same magnitude either, right? Because our velocity told us that omega A RA is equal to omega B RB. So this is true. We got that from velocity. This, you can't just go in here willy-nilly sticking an extra omega in there. Like, bad. So just remember for gears, we have this loose connection. So we have compatibility in one direction only in the tangential. Normal direction, all bets are off. They're spinning, they're pointing different ways, and they might be different magnitudes. Sure, there's a case where they're going to be the same, but not in general. All right, let's crank. So we've got a given instant. That means we're using the vector approach. The gear racks have velocities and accelerations shown. Determine the accelerations of points A and B. Okay. So I got different accelerations and different velocities of these racks on the left and right side. So as one's going up, the other's going down, and they have different accelerations. That gear is going to be doing different things. It's going to be traveling up and down as it's rotating. So we want to figure out its acceleration. I have multiple points here, so we need to figure out its angular acceleration, its angular velocity, and also track how it's moving up and down. So a whole bunch of different things to take into account here. We want to find the acceleration of A and the acceleration of B. We're going to need our angular accelerations, angular velocities to do this. Okay. So one thing to keep in mind is that A is not pinned. It can move up and down. Can't move left and right because it's kind of stuck between these walls. But it's going to have some component in the y direction. And if I just take what we have here, we've got some tracks that mesh into this. One's going up, one's going down, one's accelerating up, and one's accelerating down. We've got our radius, 0.25 feet. So I'm going to call this left side L and this right side R. So these guys are meshed, right? The little teeth here are meshed with this track. So what I'm given the acceleration and the velocity for L. So my acceleration for point L is something in the x plus a known value in the y, 2 feet per second squared. The velocity of L, 6 feet per second squared. Per second, not squared. Positive y direction. So this is what's happening on this side. Hey, we know the acceleration in the x direction. That's going to be due to that rotational rate. What's the angular velocity of the body? We don't have that part figured out yet. So we move on. The acceleration of the right side, same story. I don't know what it is in x, but I do know what it is in y. It's minus 3 feet per second squared. And the velocity, minus 2 feet per second in the y. So this is all the stuff we were given from our problem statement. So for our acceleration analyses, we know I got an acceleration of 1 point, plus I got an alpha cross r, plus an omega squared times r, or minus details. But we know that we're going to need alpha and omega. So if I need omega, I need to get this from my velocity analysis. So that's where we can start. Figure out what's the angular velocity of this guy, omega. And to do that, we want to relate the velocity at 2 points on this body. Well, I got the velocity at 2 points on the body. So we can find omega. We can say that the velocity of the left is equal to the velocity of the right plus the angular velocity crossed with the vector from right to left. Hey, we could have also used our rules for instantaneous center. I got one going up, one coming down. They share a coincident perpendicular line. So I would have something that looked like, like this. I'd have a 2 over here and a 6 over here. I could draw that. I could find their instantaneous center. And I could figure out omega. I just thought of that. I didn't do it, so we'll worry about that another day. But if we jump over here now, what do I have? I've got 6 feet per second J on the left-hand side, right-hand side. We've got minus 2, that's also feet per second, plus omega in the k direction, cross with my r vector from right to left. That's the diameter. The radius is a quarter, diameter is a half. So 0.5 feet, and that is in the minus I direction. Okay, that's just my vector between these 2 points. I, J, K. So K crossed with minus I get something in the minus J direction. So all of these things are in the J direction. 6 minus 2 minus omega over 2. Omega vector minus 16 radians per second in the k direction. So, hey, what'd I do? I drew my omega positive because I'm lazy. I take a look at this and I think, I drew it the wrong way. No big deal. Omega in reality rotates the other way, but I got a negative sign there. Life is good. But if I would have just looked at this thing and said, hey, this thing's moving up at 6 and this thing's moving down at 2, yeah, that's faster. So it's got to be rotating the other direction. So we found the angular velocity. That was our first piece. Now we want to find angular acceleration. And we'll use those same things. We know something about the right and the left point. So if I write a similar expression, but not for velocity, for acceleration, my acceleration at the left is equal to my acceleration at the right plus my angular acceleration crossed with the vector between them, right to left, minus omega squared, just found that, times my r vector from right to left. All right, so we figured out that r from right to left is minus a half in the I. We just got omega, minus 16. We know a little bit about these accelerations, and we're trying to find alpha. So plug in and see where this takes us. So the acceleration on my left side, what do I have? I've got ALX, x component in the I direction, plus 2 feet per second squared in the J, equal to what's happening on the right side, something I don't know in x, ARX, and minus 3 feet per second squared in the J, plus alpha in the K, crossed with minus 0.5 feet, and that's an I, minus 16 squared times minus 0.5 I. Whole bunch of stuff. Okay. K cross minus I, this is still minus J. So this one is minus 0.5 alpha in the J. This one, I don't have a number, but it's going to be a plus. I got minus a minus and something in the I direction. And I got 16 squared, so this is an I term. this j term, this j term. So if I pluck off the j terms, 2 feet per second squared equal to minus 3 feet per second squared minus 0.5 alpha. Only thing to find out, alpha is minus 10 radians per second squared. My I terms, I'm not going to mess with them, but if we wanted to, we could write them down. ALX is equal to A on the right side in the x minus omega squared times, I'll put a plus, omega squared over 2. That's my omega squared, and I got a half. So we know these guys are rotating. Their acceleration in that tangential direction is based on omega. We can make some leap that these guys are going to be the same, but opposite, pointing in opposite directions, because they're attached to the same rotating body, and solve for what they are. I think if you're clever, you get that. If not, you're like, the mechanics, it'll drop out in the end. So we don't need to see that right away. Okay, but we've got omega. We've got alpha. Now we want to find the acceleration. Yeah?
So for your step, just before you separate it to j and I,
Yeah.
you use that 16 squared. Isn't that in the k direction?
Yeah.
K with I?
Yep, sure. So the question is here, I got this omega squared, and omega is in the k direction, right? But if you remember what we did, I got a lot of papers now. Bear with me for 1 second as I go back in time. When we started with our expression for acceleration of b, I had omega as a vector crossed with omega as a vector crossed with r as a vector. Because omega is perpendicular to r, as you go through this cross product twice, you find that you only need the scalar value of omega. You no longer need its direction. So if you want to kind of convince yourself of that, I did that the other day, but I, j, k, right? Omega is in the k direction. So if I've got omega crossed with r, and for ease of this, r is in the I direction. So if I do this first cross product here, omega cross r, I got something in the k direction crossed with I get something in the j direction. This is omega r j, right? One more cross product. Now I got this cross with this. So now I've got something pointing in this direction. That's my omega r from the first. One more cross product, k cross j. I'm going to get something in the minus I direction. This goes to minus omega squared r in the I direction. The gotcha here is that r in the I direction is my original vector, r. Omega is now just a scalar value. So if any r you picked was in the xy plane, because omega is perpendicular to that, when you do two cross products, just the scalar value of omega pops out. So, long answer, short question, but that really is just omega, no more k. Yeah. Yeah, it's going to depend on the type of class you're in. If you're in a 2D planar class, it's going to be okay, right? Once you start looking at 3 dimensions, though, this little shortcut that we have of omega squared times r, no good anymore. You got to do the full double cross product. All right, so what we're actually trying to figure out now. I was trying to find the acceleration of A. This is what the question asked. We have already found omega and alpha, so we're kind of ready to rock here. My acceleration of A, I'm going to reference to a point I already know. For this, we had acceleration on the left and the right side. So I could pick either one. So the acceleration of left. Just as easily could have done acceleration of right. Plus alpha cross the r vector between them from left to right, or left to A, minus omega squared scalar r vector from L to A. Remember how the gears looked from the left side to the point at the center? That's just going to be our radius. So this is going to be 0.25 in the positive I direction. Acceleration of A. This guy's constrained. It can move up and down, but it can't move left and right. So that's one of these things where if we look at the problem, it'll help us see what's going on and get a little understanding. So my acceleration of A in the x direction plus my acceleration of A in the y direction, x is going to be 0. It can't move between these two gears. Equal to the acceleration of the left side, which we wrote down. Acceleration of the left side, x, plus 2 feet per second squared in the y, or the j direction, plus alpha minus 10 radians per second squared k, crossed with r. Here we're going from the left side to the midpoint. 0.25 feet I. And minus omega squared, which is a minus 16 radians per second, times again that quarter. 0.25 in the I direction. All right. So, what am I going to get if I do this in my last 2 minutes here? Y terms. Acceleration of A in the y direction. What I'm looking for. Great. Equal to, hey, what that left side is doing. That one. Plus k crossed I. I always draw this over and over again. I, j, k. So minus k. Cross with I. Minus j. So minus 10/4, right? In the j direction. And that's feet per second squared. So I get my acceleration of A in the y direction, 2 minus 2.5 minus 0.5 feet per second squared. So my acceleration of A vector is nothing in x, minus, that's 0.5, 0.5 feet per second squared, j. This thing's accelerating down. Now, the other thing you want to see is that now the x direction. If I plucked, what's happening? Here, I've got this thing physically constrained, so it can't move an x. That part's nice. The other side, my acceleration of the left side, j term, plus omega squared r. Hey, my acceleration, omega squared r, on the left side. That's what we'd expect to see. The acceleration in that normal direction is just what's happening from the thing rotating. Okay, that's a weekend for me. I'll see you guys next week.